Thanks, Mark. Good morning. I'm going to talk about the Larrabee architecture, which combines the parallelism of graphics processors with the general purpose programmability of a GPU. Now, I'm not going to talk about any particular product that might be based on the Larrabee architecture today. Instead, I'm going to give answers to three key questions. How does Larrabee meet the needs of graphics software developers? How can Larrabee be used to render standard pipelines using such as DirectX and OpenGL? And what other kinds of applications can the Larrabee architecture support? Now, GPUs started out with implementing a fixed function pipeline and have gradually added more and more programmable stages, but there are still significant limitations to the kind of general purpose programmability that you can achieve on a GPU. CPUs, over a similar period of time, advanced from supporting a single program invocation running on one core to supporting multiple independent programs, multi-threading, to supporting larger and larger numbers of cores on the same die. What software developers need is an architecture that provides the full general purpose programmability of a CPU combined with the parallelism and other special features of a GPU. And that architecture is Larrabee. Here's a block diagram. We see there's a variable number of x86-based processor cores. The x86 means it has an in-order pipeline, in-order instruction execution short pipeline. Each one is augmented by a 16-wide vector unit. The caches in Larrabee are fully coherent, as is required when you're using processor cores. And we have a bidirectional ring bus, 5 12 bits wide in each direction, which allows fast communication among the cores, the caches, and some dedicated logic blocks, such as the texture logic. And the texture logic in Larrabee supports virtual memory. Now, here's a view of the Larrabee x86-based core. If you look at the green instruction decode box, together with the 3 boxes to the left, that's the part that we derived from the original Pentium design, with extensive modifications, such as support for 64-bit integers. We also added support for 4 independent threads of execution on each core, which means that we also made the level 1 caches 32K bytes each rather than 8K bytes each of the original Pentium design. We also added extended support for cache prefetching and cache eviction so that you can, in effect, use the caches as scratch pads or as streaming buffers. But that's just a performance optimization. They are fully coherent. Your application will work regardless of what kind of prefetching you use. Next, let's take a look at the vector unit. It supports 16 32-bit floating point or 32-bit integer operations per clock. And when you use a memory operand, you can change from an 8 or 16-bit numeric type up to the 32-bit float or int format. And that happens as the data is being read into the pipeline. It also supports various kinds of swizzle operations on the memory and vector operands. But the most important aspect of the Larrabee vector unit is that it supports what we call a vector-complete instruction set. What we mean by that is that in addition to thread parallel programming, where each thread of execution explicitly chooses the work to perform on the 16 vector processor lanes, we also support data parallel programming, where each vector processor lane executes its own separate invocation of the same program. Now, there's 2 key features you need in order to enable data parallel programming. The first is you have to have the ability for each vector lane to compute its own separate memory address so that you can gather 16 separate memory reads into one vector register or scatter a single vector register to 16 separate memory addresses. The second thing you need is the ability to support each of those program invocations having its own separate conditional execution. To support that, we provide a set of mask registers. Here's an example. Suppose you write your data parallel program and you have some special case, so that a certain part of the code has to be executed differently in that case. So you create an if-then-else conditional. The way it would work in the Larrabee vector unit is you compute the if condition 16 wide, store those 16 bits into a single mask register, and then check to see if they're all zeros. If so, just run the then branch. If it's a mixture of zeros and ones, run both the then and the else branches using the mask register to decide which vector lanes are written for each of the 2 cases. And a single instruction can do the numeric conversion and the swizzling and the masking with no extra execution time and no extra latency, so this is highly efficient. Now, I'd like to draw your attention to several key differences between the Larrabee architecture and a typical modern GPU. First and foremost, each Larrabee core is a complete x86 processor with everything that implies. It supports virtual memory, page swapping, context switching. It supports fully coherent caches at all levels of the cache hierarchy and maintains the memory read-write ordering that's defined in the x86. Second, it supports efficient interblock communication by means of our wide ring bus. This is what we use to be able to implement the cache coherency. It also allows fast access between the cores and the small number of dedicated logic blocks in Larrabee. There's a lot of things that are done in dedicated logic in a standard GPU that we don't have in Larrabee. No back-end blend logic, no interpolation logic, no rasterizer logic. All that's done in software. And when a core talks to the texture unit, it does it via writes to memory, which is to say, writes to the L2 cache, and the texture unit similarly communicates with the core. What this means is you never have a case where you have to go from one programmable stage through fixed function logic to get to the next stage. It simply doesn't get in your way, and the result is much more general functionality and far more flexible load balancing. So the Larrabee architecture delivers on the goal of providing the vector parallelism of a GPU combined with the general purpose programmability of a CPU. Next, let's consider how Larrabee is able to render the standard DirectX or OpenGL pipelines. Now, back before 1996, before Voodoo 1, nearly all rendering code simply ran on the host CPU. And Larrabee allows us to return to those days. You can write any code you want and simply execute it on the Larrabee processors. But most software developers will probably want to use a standard pipeline, both for simplicity and for cross-platform support. In Larrabee, the standard pipeline, every stage is implemented in software. In a typical GPU, the software stages are interrupted by fixed function logic, and that raises several issues. First, you have to decide how much performance to put in each fixed function stage. You have to decide how much bandwidth into each fixed function stage to provide. And you have to decide how large a FIFO to put in front of each of those stages to cover variations in the workload. And that's a real problem because you design this whole thing around your concept of what the typical workload is, but there's no such thing as a typical workload. We see here our analysis of 25 widely separated frames from 3 different DirectX 9 first-person shooters, and the workloads vary tremendously, even taken in the average. If you scale your alpha blender to be fast enough to support Fear, then it's mostly unused when you run Gears of War. But of course, it's much worse than this, because within each one of those frames, there'll be periods where you have large numbers of primitives that produce almost no visible pixels, or very large triangles that cover the whole screen and produce huge numbers of pixels, so the pipeline loading varies wildly from moment to moment as you're rendering. Now, current GPUs are able to trade off between the pixel shader and the vertex shader, but not the other stages of the pipeline. Larrabee is able to dynamically load balance all the stages of the pipeline, and here's how we do it. We use a method called binning, or sometimes tiling, or also sometimes chunking. The basic idea is to define a front-end processor that handles all the vertex and primitive operations and writes those results into a set of bins. Each bin is associated with a tiled region on the screen, 64 by 64 pixels, perhaps 128 pixels squared. And then you define a set of processes that read from those bins and process all the pixels in each of those tiles. Now, each of the orange boxes on this figure represents a separate independent processor core. Since they're independent, they can run different programs. In fact, a single processor core in Larrabee might render tiles for a while, and then the next task might be to render a vertex buffer, or perhaps to do physics or some other operation that the software developer would like to perform down on Larrabee. Let's take a closer look at how the tile processing is done in the back end. So, each core supports 4 independent threads of execution, meaning they can run completely independent programs. So we divide this up by dedicating one of the threads to do setup operations. It reads from the bins, does interpolation, scoreboarding, and other such operations. The remaining threads perform the actual pixel processing, depth test, the pixel shader, and the alpha blending. No fixed function logic anywhere in the back end. Now, the fact that the alpha blending is done inside this code means that it's perfectly natural for Larrabee to expose a feature that software developers have been asking for years, which is to have access to the frame buffer values as they're writing their pixel shader. All we have to do is find a way to expose that in a standard pipeline, and software developers will have that feature. Now, when we're processing a tile in one of these cores, the first thing we do is we prefetch the pixels of the tile into the L2 cache. And the result is, imagine you have a scene that has a very high depth complexity, so that even after doing your hierarchical Z calling, you still have, say, an average of 3 accesses to each pixel. Now, in a typical GPU, that would mean you have to do 3 accesses to external memory in general. In Larrabee, you do 1 access to external memory, 3 accesses to the L2 cache. And the result of that is that Larrabee uses dramatically less memory bandwidth than immediate mode rendering on the standard pipeline. Here we see our analysis on the 25 frames for each game, and we've sorted them by the amount of memory bandwidth required in immediate mode. In immediate mode, we're assuming perfect hierarchical Z calling. We assume 1 megabyte depth and color caches and use of compression. In binning mode, we are counting the bandwidth required to write data to external memory into the bins and read it back again for use in the back end. And yet, for Half-Life 2 Episode 2, the frames take about 1.7 times more memory bandwidth in immediate mode. For Fear, 2.5 to 7 times more memory bandwidth. Every frame takes more memory bandwidth in immediate mode than in Larrabee's binning method. And since memory bandwidth is one of the important factors to cost and power and ultimately performance of a system, that's a dramatic performance benefit for the Larrabee architecture. Finally, it's important to consider the scalability of Larrabee's software renderer. We did tests ranging from 8 cores up to 48 cores, and for our 3 sample games, we got scalability within 10% of perfect linear scaling. Now, the first time we plotted these numbers, it turned out that Fear was actually falling off by 18% rather than less than 10%. So we looked at the data and we discovered that when you're running Fear, there turns out to be one really, really large vertex buffer. And when we were processing that, we started running out of work to assign to all the cores. So we turned on a feature that we'd already implemented, which was to take large vertex buffers and just split them up into 200 vertex sections. Then those multiple sections are able to be processed in parallel in the front end, and the result was it scales as you see here. So the fact that Larrabee supports a completely software rendering pipeline means that you can modify the pipeline, the renderer's scheduling and other features to match the particular workload of your application. Now, with a typical GPU, some aspects of the design were frozen in silicon potentially years before you even wrote your application. So we can see that Larrabee provides an efficient and scalable way to support standard software renderers such as DirectX and OpenGL. Finally, I'm going to talk about other kinds of applications that Larrabee can support. Now, I mentioned one example already of extending the rendering pipeline, so you'd write your code to DirectX or OpenGL but have a backdoor way to use an extra feature. Here's another example, transparency. Now, transparency requires sorting the translucent surfaces so that you can combine them together in back-to-front order. But that's not enough, because what if you want to then do a multi-pass effect where you add lighting or shadowing, or perhaps you add patch fog to some region of your rendered scene? If you've already resolved the translucency, then you get an example as you see on your left, where the small dragon is almost completely hidden in the fog when seen directly. But when seen through the large dragon's wing, it pops into view because the depth at that pixel is the depth of the large dragon's wing very near the viewer. If we maintain an A-buffer type structure, if we keep multiple values at every pixel and then do fog processing based on those multiple values, we're able to render the scene correctly as you see on your right, where the small dragon is equally obscured by fog, whether you see it through the wing or not. And support for this kind of irregular data structure is something that Larrabee is able to provide for software developers. Here's another example. A basic shadow mapping algorithm works essentially by drawing the shadow from the point of view of the light source and then warping that result to paint it onto the image. The problem is that the warping stage can greatly enlarge the shadow, resulting in exaggerated pixel edge artifacts. Johnson et al. In 2005 produced an algorithm called irregular z-buffer. And in this algorithm, all of the shadows are rendered at the resolution of the screen. And so you don't have these pixel edge artifacts. However, as the name suggests, irregular z-buffer requires irregular data structures, and it requires adding stages to the pipeline. So the result is that Larrabee is able to practically support irregular z-buffer as an extension to the standard rendering pipeline. Next, let's consider data parallel programming, as I mentioned before. Now, the key idea of data parallel programming is exemplified in APIs such as DX11's compute shader or OpenCL, among others. And the basic idea is you have an array of parallel program invocations. And within each invocation has its own separate data. And within that array, you define groups so that all the invocations inside one group share a set of local memory registers. And the purpose of that is to reduce memory bandwidth required in the same way that we reduce memory bandwidth by prefetching the pixels from a single tile into L2 cache when processing back end of the rendering pipeline. And so here's how you'd map this onto Larrabee. First, you create something called a fiber, which executes a large number of these program invocations, which we call strands. Now, in the compute shader, they're called threads, but we're already using the word thread for something else, so we call them strands. And you would, in a single fiber, you'd execute 16 strands, one per VPU lane, or possibly you double pump or triple pump the VPU. The reason you do that is if you have, for example, a short program and you have lots of unused instruction slots due to register dependencies. Then, inside one of your hardware threads, you sequence through a series of 2 to 10 fibers. So you'd run one fiber till it does some long latency operation, such as a texture fetch. And then you simply save out the registers for that fiber, copy in the registers for the next one, continue executing fibers until you've allowed enough latency time to pass such that you can go back to the original fiber and continue executing it. And finally, all of the strands in a single group execute on the same core. And the result of that is that their shared memory doesn't require extra registers inside the Larrabee architecture. They can simply treat those as memory accesses, which are contained in the L2 cache. And so all the strands that run inside a single group can very efficiently exchange data, perform atomic operations, and with proper synchronization, one can write and the other one can read the data, all entirely within the single core and its L1 and L2 caches. Now, a lot of things about what I've described here are actually very similar to the way that data parallel programming is mapped onto typical modern GPUs. There's two key differences. One is, as I said, we don't need any extra hardware in the design to support this. We don't need to add 32 kbytes or whatever of extra register memory. We're already using the L2 cache. But the second key difference is that all of your scheduling choices are under software control. And that's important because generally the number of strands you want to have executing in parallel is the minimum number necessary to cover your latency. And so with Larrabee, either the compiler or the software developer directly can control all of those choices about how the code executes. Finally, we have an even more general way of programming Larrabee. Larrabee will be able to run a virtual memory operating system to handle paging and so forth. You can see from the software stack it will support DirectX and OpenGL, compilation and performance tuning and so forth. But we also have an interface called Larrabee Native. That allows you to write C and C++ programs and run them on the thread and core of your choice inside a Larrabee chip. Now, when I say C and C++, I don't mean C-like syntax. I don't mean a subset of C. I mean C, C++. If you can write it in those languages, you can run it on Larrabee because they are actual x86 processor cores. So here's an example, and you can see more details of this in the paper, of a variety of non-graphics applications where we tested the scaling over numbers from 1 to 64 cores. And the top line on that is actually a 3D fast Fourier transform. It scales nearly linearly across that wide range. There are some that start tailing off as we get to large numbers of cores. And the thing to do with those is to study the application and determine, is the problem the fact we're simply scheduling badly and we aren't able to use lots of cores for that reason? In which case, change your scheduling over them. Or is the problem that our particular algorithm isn't exposing enough parallelism, in which case you have the opportunity to change the algorithm because the entire pipeline is done in software and is under the developer's control. So, in conclusion, I've shown that the Larrabee architecture combines the vector parallelism of a GPU with the full general-purpose programmability of a CPU, including virtual memory, paging, all those modern conveniences. Secondly, Larrabee supports efficient and scalable implementations of standard DirectX and OpenGL pipelines. If it runs on DirectX, it'll be able to run on Larrabee. And third, Larrabee is flexible and programmable to support a wide variety of applications, including applications that support irregular data structures. Now, as you listen to the rest of the talks in this session, and in the rest of SIGGRAPH, I encourage you to think about the possibilities that the Larrabee architecture enables. And we who are working on Larrabee will be really excited to see the applications that you invent for the Larrabee architecture.
So Larry's going to be joined up here by two of his co-authors to answer questions. I'll kick that off with one question while some of you make your way to the microphone if you have some questions of your own. So if you're programming Larrabee as a parallel processor, what support do you have for some of the common parallelization primitives, in particular synchronization between the cores and primitives like a scan primitive, which is quite common in parallel processing applications?
Tom, do you want to answer that? Well, basically, if you can do it on an x86 processor, you can do it on Larrabee. Is the short answer. And
but between it's between the processors, synchronization, say between the processors.
Okay, Steve Junkins, would you like to take that one?
Questions about scan primitives.
How to synchronize
just
between
parallelization
cores.
primitives like synchronization between cores and things like scan operations between cores.
So there's it's standard x86 programming, so there's no built-in primitive for scan primitives types things, but there's standard increment and decrement atomic operations, and you can build those things basically out of those building blocks.
What about synchronization?
Do you want to take the synchronization one?
Well, so we support the full existing library. We support the full existing library of.
Or see if that works.
So we support the full library of standard software development tools for multi-threading and synchronization and so on. Thread building blocks and such.
And we support lock operations, for example, across multiple cores, using the ring bus once again.
Question here?
Yes.
Could you please state your name and affiliation when you ask a question?
Thank you. My name is Torolf Tenjen. I'm from Norway, and I'm a graphics programmer, and I'm wondering how many teraflops does it yield that you have observed, and what's it going to cost?
Well, as I said at the beginning, we're not talking about specific products right now. That will come later. But a single Larrabee core supports 16 floating point operations per clock. And you'll find out when we announce products what the actual clock rated number of cores are. But the architecture supports a wide variety of implementation configurations.
I was afraid of that.
Yes, well.
How about in the middle here?
I'm Bruce Bell. I work for Blueshift. I'm a graphics programmer, and I recall you were talking about swapping out the context of one thread and bringing in another, but isn't there a trade-off between the sheer size of your register set, which is a good thing unless you want to swap it out, and could you talk a little about that and what decisions you've made and what kind of performance you can get for a full context switch?
Okay, so what I mentioned was that within a thread, you can swap between multiple fibers, and that just involves saving out the registers the fiber was using, then copying the registers the previous one was using. Since the architecture is dual issue, you can do those, the swapping out and changing in parallel in many cases with the vector execution. So we've actually found that it's very efficient.
The other trick is that the compiler gets to choose where it swaps out. So it generally chooses a point, where you have as few live registers as possible. In practice, we see 4 or 5 registers being swapped out. It's remarkably little.
Let's go over to the far aisle.
Andrew Garrard, 3D Labs. I just wanted to ask, you say the cores themselves are in order, but the memory operations, sorry, I sound really different on this. The memory operations, you have multiple ones in flight when you've got multiple fibers being switched between. I just wondered if you could comment on what restrictions you have on how many are in flight at once.
Hardware restrictions?
The number of fibers is, so fibers are purely a software construct. So you're limited by, can you keep all that working set in cache? So you can have as many fibers as you want. In general, we find 2 to 10 is a reasonable number, and obviously you want that number as low as possible, not as high as possible.
If you want to take a number, I said you could have as many as 64 strands per fiber and say 8 or more fibers per thread, 4 threads. And so multiply that out. That's the number of strands you could support if you needed to in a single core.
But are you limited by the hardware, by the number of memory operations you can have going at once?
When you're talking about swapping between fibers in a thread, you wouldn't have multiple memory operations actually outstanding at the same time.
To high latency for a texture access, for example.
Oh, I see. For texture accesses, how many in parallel?
It's enough to hide the latency.
Yeah. I mean, the thing is that we write to memory to store up the pending operations to the texture unit. So it's not a great problem. You might run out of memory.
All right, and let's go with the last question. They will be up at the front afterwards for more questions, but let's go with this aisle here for the last question.
All right, I've actually got sort of a couple of questions, so I'll try and make them short. So one, my name is Gabriel Stater from Transgaming. What is the relationship between the Larrabee vector ISA and AVX is one part. The other question is, other than texture sampling, do you have any other fixed function units?
Okay, the first part of that, we'll be talking more about specific ISA issues at a later time. That's related to the product announcements, so we're not going to talk about that today. However, I'm sorry, the other question was?
About fixed function units.
Okay, so the fixed function units in the architecture are whatever the particular implementation needs. Obviously, you have a memory controller, you have a display controller. There's other things that if you need it in a particular implementation, you'll have. I mentioned texture units because that's the one you absolutely have to have, because if you tried to do the texture operations on the core, it would be about 12 to 40 times slower due to the fact that texture requires these unaligned 2x2 axes and filtering and so forth.
The other fixed function units are rather less exotic things like DMA controllers and standard things that kind of have to be there in a system.
Transcendentals, anything like that?
They're in the core.
Okay. All right, thank you.
All right, let's thank the authors again.
Thank you.